according to the four fundamental forces, one of which is the electromagnetic force, charges attract or repel. If they are like charges, they repel, and if they are opposite charges, they attract. What Coulomb studied was the relationship between that force and how strong it is. And what he found is the force between the two charges is directly proportional to the magnitude of their charges and inversely proportional to the square of the distance between them. Written mathematically, force for a charge is proportional to the multiplication of their charges, Q1 and Q2, and then inversely proportional to the square of the distance between them. We call this distance between them the radius, because you can imagine that if I had a charge here and I had a charge here, the distance from here to here is arbitrary any way around an entire circle. And so if it was over here, the same distance away, you would get the same force. The direction would change as a function of where it is in space. So this equation written with an equals after doing some doing experimentation to determine the proportionality constant yields a force equal to what's now called K times Q1, Q2 divided by the radius squared. This is Coulomb's law, and what you'll notice is that it is a scalar. There is no direction on this force. That is because it is dependent upon where the charges are in space. And so the direction of this force is assigned by you, right? The direction is determined by your frame of reference and by your knowledge of like charges attracting and opposite charges repelling. So best practice while putting in charges here is to use absolute values for their particular values, which protons and neutrons, or protons, electrons, any charged particle has a known value based on the elementary charge, which is the charge of an electron. 1.6 times 10 to the negative 19th coulombs is the charge of one electron. A proton would be a positive value of that, and then any other charges would be an integer factor of that particular value. Normally these charges will be presented as long as they're given in coulombs as the unit. The complex unit, which we will talk about when we do a little bit more of electricity, and the radius is listed in meters, then K, as Coulomb's constant, happens to be 9 billion, 9.0 times 10 to the 9th, and then the units are newtons times meter squared divided by coulombs, capital C squared. Sorry. So a simple experiment would be to put two electrons separated by a small distance, let's say 50 centimeters in space. And we're asked for the force on electron 1 in comparison to electron 2. Electron 1 being negative and electron 2 being negative, of course, right? This is E minus. These two things are going to repel. So the force on 1 due to 2 is going to be this way. This is the force on 1 due to 2. And then, of course, thanks to Newton's third law, equal and opposite, the force on 2 due to 1 is going to be this way. Now, again, as I said, we cannot assign these directions based on positives and negatives because, of course, if I put two negative values in, I'd multiply and get a positive, and that wouldn't make sense for my direction. So best practice is to use the absolute value, the scalar value of the charge, when solving. So to calculate the force on 1, the force on 1 due to 2 is going to be the proportionality constant, Coulomb's constant, times charge 1 times charge 2 divided by the radius of separation squared. Of course, this is 99. This is 1.6 times 10 to the negative 19th times the same, 1.6 and 1.6 squared. Again, with no sign, divided by the radius of separation listed in meters, 0.5 squared. Running the calculation 9 billion times the charge squared divided by 0.5 squared, I end up with 5.76 times 10 to the negative 9th newtons. This is the force between the two charges, again listed as a scalar. So if I'm looking at a linear problem where this direction is defined as positive, then in this particular case, force on 1 due to 2 as a vector is going to be negative 5.76 times 10 to the negative 9th newtons. This answer is only appropriate given the frame of reference that was listed above, so it's problem specific.